can be looked at as kind of standard. This pen standard multiplication. And the other one is pointwise multiplication. I wonder if I can hold this pen a different way. There's this little button on the pen that I keep pressing that keeps it from writing anything. So, so going back to the point is that when we do Fourier transforms to compute products, what we do is compute the Fourier transform of x, we compute the Fourier transform of y, we do our pointwise multiplication, and then we invert it, which we can see if we want to write this out. The full process is compute, let's say x prime equals the Fourier transform of x, y prime equals the Fourier transform of y. We do pointwise multiplication, which we can represent as x prime, maybe a little circle with a dot, y prime, and then we get, let's say, z prime, and then our final product z equals the inverse Fourier transform of z prime. That's the whole process of multiplication. Like I said, we can overflow. Let's say that we're working in base 10, which is what normal arithmetic is. If any of our numbers went over 10, then we're overflowing our base. And we want to make sure to avoid that. So if we write down the definition of convolution, all we need to do is avoid a base or a modulus that would lead to overflow. So let's look at that. So the definition of convolution is something like this. Let's see. Convolution is something like this. If we have two sequences x convolved with y, this is equal to, for a discrete convolution, we go from I equals 0 to n minus 1, and we're computing x sub I times y sub n minus I minus 1. So we don't want this computation right here to overflow our integers. So this can possibly overflow. And we want to make sure that we avoid that. Well, it's simple. If we know what x and y are going to be around, then, well, we do know that. If we're working in a numeral system where things are base b, then the following inequalities are satisfied. We'll have 0 is less than or equal to x, I, which is less than or equal to, less than or equal to, which is less than or equal to b minus 1. Likewise, 0 is less than or equal to yi, which is less than or equal to b minus 1. So we can, if we were in the absolute worst case, we'd have a sum of b minus 1 times b minus 1. Let me write worst case. Sorry I didn't see this window earlier. Am I a student? No. I'm a software engineer that just likes to write math software sometimes. So this b minus 1, b minus 1 is the maximum, and if we sum this from I equals 0 to n minus 1, this is the same thing as having n times b minus 1 squared as the maximum possible. So So we can say the, did I get a computer science degree? No. I actually never went to university. That was just a choice that I made. But I am intently interested in computer science a lot. So this is the largest possible is this. So yeah, a lot of the streams seem to be more about I don't know, game development and so on. A lot of them are, you know, people are interested in game development. And so, and game development can be fun to watch because it's very graphical and so on. Unfortunately, I'm no expert at game development, and so, I mean, I know some things about math, and so that's kind of what I code. And so the math I'm going over now, of course, is a few little preliminaries for the bigger application that I'm writing. I'm afraid, however, that math isn't going to attract many listeners in the stream just by virtue of being kind of boring to a lot of people. But it's interesting to me, and that's what matters, I guess. So the largest is this, which means that if we're doing convolutions using our number theoretic transforms in the ring or field of numbers z over quotiented out by mz, our modulus must be greater than this right here for it to not overflow. So that's one constraint. So we can say that constraint number one. Constraint number one is that our modulus must be, whoops, I did not mean to cross that out. I meant to underline it. Our modulus must exceed that. So n b minus 1 squared should be should be less than our modulus. Our second constraint is that all of this must be less than the word size. So b and m must be less than or equal to our maximum representable integer, which is 2 to our word size plus 1 minus 1. It might be a good idea to write down all these definitions now. Of all these variables, we have x's and y's and b's and q's and, you know, whatever. So we have n is our transform length. N equals transform length. Let's see, b is our numerical base. If I can write numerical. I'm still getting used to this tablet, which I'm not very good at writing with. M is our modulus. And what else? I think that's it. Oh, W. W is our machine word length. So, for example, that could be 32 or 64 or whatever. So yeah, all of this stuff establishes a bound. We can be more conservative in some ways. We can always make the bound tighter or looser, but this is good enough. So let's see, let me think. Yeah, okay. So when we find moduli for our transform, we need to make sure that our modulus satisfies this property here. Now, ideally, there's nothing wrong with this. Our modulus can just be as big as we want. So the practical considerations, if we want to call that, practical considerations. There's no reason why our modulus can't be as large as possible. So M is as big as possible. That we can represent. So again, the constraint, the thing that constrains this practical consideration is this inequality right here. The other thing we need is the fact that our transform length n should divide our modulus minus 1. So typical moduli are equal to some prime factors m1, m2, m3, up to mp times, critically, 2 to the power of some number, let's say q, and plus 1. So what this means, and n also for our number theoretic transform has to be a power of 2. So 2 to the power of our transform length, not transform length, but the, what would you call this, the log length, has to divide, you know, m1, m2, mp, 2 to the q, which is fine. So that all that means is that this L has to be smaller than or equal to this q, which is easy. This is an easy constraint, so I'm going to say that easy. And almost trivially satisfied by most of the things that we're going to search for. So, all right. So where does this leave us then? What we want is to be able to compute a base that we can suitably use. So all of this work is to answer the question, what base and transform length, xform length, can we use to multiply two, let's say n decimal digit so the practical constraint is that we don't exceed the modulus. So we choose a very, very large modulus, and let's look for moduli now. Let's find it. What did I just work with? So if I do find suitable moduli, this is going to find a modulus for a transform of a particular length. And this function is going to, where did I put my pen? This function, find suitable moduli, is going to search for moduli that, if I can, this stupid button keeps annoying me. The find suitable moduli function will look for moduli that satisfy this property, but it will not do anything here. If it can't find one, then we're out of luck. So, but this transform length is the length of the transform assuming a particular base. So let me move over. Do I do programming for a living? Yes. Yes, I am a software engineer by trade. I keep losing my pen. So find suitable